Looking at our planet from space, it's not hard to understand why Earth is commonly referred to as the blue planet. Yet the appearance of abundance can be misleading. It has been estimated that the amount of fresh water available to meet the needs of humans and freshwater-dependent ecosystems is in the range of 0.01% of all the water on Earth. This minute proportion of water would be more than sufficient to meet all human needs, if only it were distributed in accordance with the global population. Many heavily populated regions lack abundant fresh water, and some that do are prone to cycles of drought. 1.2 billion people currently live in areas of physical water scarcity. A further 500 million are vulnerable in the immediate future. Agriculture is the main usage of freshwater by humans. As agricultural demand is expected to increase 50% over the next several decades, the number of people living with water scarcity could dramatically rise. Therefore, irrigation has a central role to play with respect to managing limited water resources. The increased yields it brings will be essential to meeting the basic food needs of a growing population. However, there is a range of negative environmental and socio-economic impacts associated with current irrigation practices. Irrigation in many parts of the world is withdrawing water from lakes and rivers faster than these can be replenished. The widespread damming of rivers for irrigation water also leads to tremendous water losses through surface evaporation, a problem made worse with climate change. Some of the world's largest rivers no longer reach the ocean for extended periods of time. Irrigation can also lead to salinization, a process which causes increases in soil salt content. In order to significantly reduce these environmental impacts while also meeting growing demands for agricultural output, we must obtain more yield with less water. A key way of doing this is to move towards precision irrigation. Precision irrigation implies reducing excess water use and wastage by delivering only the necessary amount of water to crops at the optimal time. It can vary substantially both in terms of complexity and water savings. On one end of the spectrum, it can take the form of computer-driven systems that use ground sensors to measure water content at the root level of crops across a field. This information is subsequently used to deliver water directly to the roots via a network of pipes that release only enough water to bring soil moisture up for the particular stage of growth reached by the crop at that time. At the other end of the spectrum, it can take the form of a buried pipe with perforations that is attached to an above-ground bucket through which water is added and distributed along the length of the pipe by the force of gravity. Between these two technological extremes, one can find many other forms of precision irrigation, the common goal of which is to reduce water use by delivering it in the most efficient manner possible. There are many technical, social, and economic challenges for precision irrigation to be widely adopted. Every context that precision irrigation is used will be different in terms of geography, crops, climate, economics, technological capacities, and others. Major research initiatives, development programs, and technological breakthroughs will need to be undertaken to make sure that the promise of precision irrigation can be applied to these varied contexts. The world will require these efficiencies in its use of water if we are to meet agricultural demand without stripping away the planet's capacity to maintain human life.